Oh,
Go
hello.
for it.
Hello. Good evening, everybody. Welcome to DSOLG, our December online version. And you can see Steve's with us tonight. Yay. Because we're virtually.
Finally.
Finally, Steve's with us because we can join virtually. So um, I'll just introduce basically the general introductions and we'll flow through. This should be fairly quick tonight. But if you move on to the next slide. He's got slide control. Hey, yeah. So there you go. All four of us. And you see all of us in the virtual flesh here as well. If you want to get in touch with any of us, we're all on LinkedIn. You can message us on LinkedIn directly. Or if you want to get hold of us as a collective, then if you move on to the next slide, these are the ways you can do it. The best way to get a hold of us, though, is through the email team@dsolg.com. If you've got any ideas, any suggestions for future events, any feedback, if you want to become a speaker, which we'll talk about in a bit, you can just drop us an email and we'll pick up that email. Any one of us will pick it up and we'll get back to you. Otherwise, getting hold of us through Meetup, which hopefully is how you found us tonight. We have a LinkedIn page, which we're broadcasting this on tonight as well. And YouTube, of course, which is where we're broadcasting this event this evening. And we have a podcast. Next slide. DSO Overflow podcast. It's a monthly podcast where we try to speak to some of the guests that have been on DSOLG. We also have some special guests in the past. We've had a few, like John Willis has spoken to us, and we will continue to do that over the next 12 months. And very grateful for our sponsors for helping us do this as well. So I'll hand over to Jess.
Hello. So we are lucky to exist in a whole ecosystem of meetup groups that are always doing some fun and exciting things. I'm still coming back from B-Sides London, had a great time there. The team put on an excellent session. But I hear the B-Sides Basingstoke team, I think, are looking at doing like a pub quiz in the new year. So keep an eye out for that on Meetup. London OWASP chapter are kicking off the new year with a really cool meetup with Tanya Janka from SEMGREP and Dr. Katie Paxton Fear from Traceable. So that should be really good. That's going to be on the 15th in Holborn. In Just Eat's headquarters. We've been there before, so it might be familiar to a couple of you. And I believe the BCS meetup will be doing something in the new year as well. But as always, join these meetup groups and catch up with what they've got going on.
Can I add something as well? If anyone's living in Kent, I don't know how many of you do live in Kent, but B-Sides Kent is starting off in March. It'd be the first event.
Yeah.
Takes place in Folkestone. So if you are living in Kent, just go along to Eventbrite, look up B-Sides Kent, and look forward to seeing you in March.
Very cool. Aha, it's my turn. DevSecOps London Gathering wouldn't be as successful as it was if you've experienced 2024. It's been a fantastic year, an amazing birthday, a wonderful boat trip, boat party, and all of this is down to our amazing sponsors. First of which is Prisma Cloud, a cloud-native application protection platform. If you start with cloud and you end with code, this is the thing you want to check out. Apiro, an application security posture management, kind of the opposite side of the same coin, CNAP versus ASPM, depending on your perspective. One of these or the other might be perfect for you. Ability to inventory your application, prioritize business critical risks, and of course, measure, prevent, and reduce application risk. More at apiro.com. And finally, Tigera. You probably know Tigera by the cute little cat down there at the bottom. That is Calico, one of the most popular Kubernetes CNIs. And from there, building upon that, they have an entire platform for protecting, detecting, and mitigating security breaches. So if you are doing a bake-off between vendors, depending on your application security requirements within Cloud Native, I think you should get both of these in and take a look, or all three of these in and take a look.
And this is not an event without our speakers. We've had some incredible speakers throughout this year and another one joining us this evening. And next year, we already have some brilliant speakers lined up from January through April, but we are always still on the lookout for extra speakers, whether it's a lightning talk or a main talk. We love to hear from the community. So you can scan the QR code, you can message us at team@dsorg.com, you can suggest your topic, your synopsis, or just get in touch with us and we can have a chat about how you might want to become a speaker to join one of our live events next year. And finally, before we kick off this evening, the plans are already in action for next year. Our first event will be live on Wednesday, the 15th of January at Next Gen Cloud, which is not far from Farringdon. And we have 2 speakers that evening with a lightning talk and a main talk. So save the date. We'll be sending more information out over Meetup. It's already live there, so you can find it either on Meetup or through the QR code now. And we'll be back in person from 6 o'clock on the 15th of Jan.
Okay.
So our
It's time to
speaker
bring on a
tonight.
speaker.
Yeah, so we're going to introduce our speaker for tonight.
And I will.
François, it's over to you.
We're going to hand over to you, Francois. I'm going to duck everybody out and
all right,
big you up.
Thank you. Thanks for having me. Can we get my slides up? All right, perfect. Well, thank you so much for having me. I hope the sound is all good on your side. Maybe before I begin, quick poll of the audience just to make sure that the chat comments and all that flows through. Quick poll: who here uses Terraform either frequently or daily, or even just has used Terraform in the past? I'll go on. I don't know how fast the comments can come in, but also I'd be curious to know if many of you are using any kind of CI/CD platforms on a regular basis. For instance, GitHub Actions, because that will be relevant for the rest of the talk. So so if I start my actual presentation, my name is François Proulx. Let's just check the slides. Okay. My name is François Proulx. I'm Senior Product Security Engineer at Boost Security. Boost Security is a Montreal-based startup, so Montreal, Canada, that is. I also lead our supply chain security research team, and that's going to be the focus of the talk. I can actually see some of your comments coming in. Thank you. So the backstory behind this talk is that when we typically hear about supply chain, we're mostly talking about the risk management of known vulnerabilities, so typically CVEs, and that area of supply chain is quite mature by now. We're talking about producing an SBOM, that is an inventory of the dependencies that we use to build our software, using tools that would be kind of called SCA, to basically software component analysis that would effectively highlight the known vulnerabilities in those dependencies. Overall, the tooling, the data around that area of supply chain is quite mature by now. It's being used more and more at scale, even being mandated by some governments, not to mention the US government. If you want to be a supplier to US government, it is mandatory now to produce an SBOM. And that's, spreading all around the globe. I'm sure in Europe also that's being discussed quite a bit. Also, when we hear about supply chain, we hear it in the context of malicious packages being published to various package ecosystems such as NPM, PyPy, Docker Hub, and others. But in most cases, those kind of compromise are typo squatting. So basically, you take a very popular package, you add a backdoor to it, and you publish it again in the same public registry with a slight typo that would be easy to make when you do like pip install, for instance. Also, scenarios of dependency confusion. So you might have dependencies that are meant to be only consumed internally. So you might have a team producing an internal library, another team consumes it, and it's not meant to be published publicly. But if someone, an ex-employee or someone effectively guesses your internal naming scheme, they have an opportunity to publish a package, a different package, a malicious package with the same name in public registries. Then you end up with a confusion depending on how your CI/CD systems are configured. They might prefer to look up that name first in the public registry and then pick the wrong one, which is potentially compromised. Also, most of the time we're talking about scenarios where there's been some kind of credential stealing, password cracking, or just tokens, API keys to publish to NPM, for instance. And, last spring, I'm sure you've heard about the XZ project, a well-known dependency of Linux. In that case, it was, in fact, a dependency closely related to OpenSSH, which ended up backdooring SSH process in Linux through this compression library, which in that case, it was more like a rogue contributor to a legitimate popular package that over time they gained the trust of the community and added some malicious code to the package. But when it comes to the build pipeline of the same open source packages, our intuition, my team's intuition, is that it's not as much on most people's radar. There are a number of resources that have been published over the past few years, namely the OS CI/CD Top 10, which is a really good resource if you want to learn more about protecting, hardening CI/CD systems. But in our mind, this resource is a bit more of an academic exercise, where my feeling is that they kind of wanted to fit the top 10 list, and it's a bit stretched to fit 10 issues, but it's still a good resource to know about. Also, when it comes to the build pipeline, again, there's no such tool to produce an SBOM. Unlike the SBOM tooling for regular software, when it comes to the build pipeline, there are also plugins and other dependencies that come into play, but there's no easy way to produce the list of those dependencies. When you look at the various plugins, so for instance, GitHub Actions as kind of basically a sort of plugin mechanism, there are a few CVEs, but really very little. Like if you look at CVEs that are specifically labeled for GitHub Actions, there's no more than 20 or 22 maybe if we look today. So some months ago, it was literally 20. And our intuition is that it really cannot be the case that there are only 20 vulnerable GitHub Actions out there, given that there are well over 45 or 50,000 public GitHub Actions. So the agenda behind this talk is that we'll start by telling you how to threat model, build pipelines, how to analyze the vulnerabilities in those build pipelines, how to find the vulnerabilities and how we basically found it at scale in our case, and how to fix the different vulnerability classes. So let's start by threat modeling. First, before we begin threat modeling, we need to have a common terminology. And what's a great resource that exists is the SALSA framework, SLSA, which stands for Supply Chain Levels for Software Artifacts. It's an open source threat modeling framework published by Google under the Linux Foundation, kind of closely related to Open Source Security Foundation. You can find it at salsa.dev. And one of the main artifacts of the SALSA framework is this diagram, which has an inventory of threats. And it's interesting to just kind of model a typical software delivery, development lifecycle. So on the left side, you have someone writing code, typically a developer on their laptop using Git to effectively get a commit and push the code to a central source control system, most likely GitHub or GitLab or Bitbucket. And typically in a source control system like GitHub, you would have a pull request where developers have the opportunity to review the code contributions. And those can come both from fellow contributors in an internal, like in a commercial setting, but also in the context of open source, you would accept contributions via pull requests from forks. then typically there will be some kind of CI/CD system that will automatically kick in and run tests. So it could run, for instance, linting, formatting checks, and effectively just a test suite, unit tests, integration tests. In many cases, the CD part of it, the deployment part, will end up publishing a package, an artifact, which will be stored in some kind of package registry. So it could be in a commercial setting where you would have a Docker registry, maybe an AWS ECR. And ultimately, on the consumer side, the right-hand side, you would have maybe a Kubernetes cluster that is effectively running those Docker images as pods. The same idea would apply just as much to other packages published to NPM or PyPy. But when we focus on the build part of the Salsa framework, we see that not only the dependencies come in at that time, they are pulled in so that they are part of the final artifact, but there are also build time dependencies that are not part of the final artifact, but they are definitely at the runtime during the execution of the build. And similarly to other dependencies, you will have direct intransitive dependencies that may be used, for instance, only to execute tests, and they are not necessary for the final artifact. At the bottom, you see a number of threats that Salsa highlights. And for the rest of the discussion, we'll be focusing on what is relevant for the build threat. So basically, ultimately, the attacker's end goal would be to compromise the build process in some way, most likely to publish a compromised package that, could also be put directly in the package registry in the context of kind of stealing credentials to push directly to NPM, for instance. And ultimately, most of the time, it's really about adding some malware. So if we open Pandora's box of build pipelines, most people think about the SolarWinds breach, which happened around the year 2020. And in that case, SolarWinds was a commercial product. But the same idea, the same type of breach that happened for SolarWinds applies just as much to open source packages. So any open source package that you interact on a day-to-day basis, either in your operating system, you use a apt to install some Linux package. You use a pip to add dependencies for your Python projects. You use Docker, Docker run, Docker pull, or on Mac Homebrew. All those are open source packages that you pull in and more or less blindly execute the code that was most likely built in some build pipeline. So when we look at those build pipelines, they're often very complex, very hard to analyze their behavior. There is, again, unaccounted components. So basically those plugins and other like build time components that it's very hard to even keep track of them. You still see a lot of curl pipe bash, so basically pulling arbitrary scripts and blindly executing them without performing any kind of cryptographic signature verification. And most of the time, the build tools, the tools that run in build pipelines, so compilers, linters, and test tools, they were never really designed with secure by design principles in mind. They were typically designed at a time in the 1970s, 1980s, when it was just compiling source code from trusted environments, and certainly not considering that there could be malicious input passed to those compilers. But overall, build pipelines produce artifacts which are running in production. So we think that the build pipeline is just as important to secure the overall system. So for the rest of the talk, I'll be focusing on scenarios that are applicable to GitHub Actions, but the same idea would apply just as much to GitLab or Bitbucket or other systems. And also, it will be mostly for scenarios that are relevant for open source projects that have a public repo. So keep that in mind. So here, the typical attack scenario we'll be looking at is what is called pull request. So you have a pull request, and that would be effectively abusing that to compromise the artifact. So what you need first is a public repo that is using GitHub Actions, and a GitHub Action workflow that triggers on opening or making modifications to a pull request. And there are different events related to that, but those that we care about for the attack scenario is pull request target and workflow run. Later, I'll discuss others that are also risky. Then you want scenarios where there are some kind of secrets that will be used by the build pipeline. Because if there is no secret, really, there is not much to be stolen, given that it's a public repo already. So the source code is not considered kind of intellectual property relevant, unlike in a commercial setting where the IP itself would be relevant to protect. So we're looking for secrets, and in order to do that, we need some kind of remote code execution, which could come in the form of some injection, which is typically in Bash, or abusing existing build tools used by the build process. The attacker's end goal would be to exfiltrate the secrets that are at runtime so that they can compromise the artifacts. The actual attack tree that we have built internally, and that one is solely focused on GitHub Actions, is much more complex. There are a number of mitigations that someone can put in place, and the attacker has more options to circumvent some of those mitigations to achieve their end goal. So if we look at vulnerable workflow, we notice that this workflow is triggering on pull request target event. Also, it does not explicitly specify the permissions, so they would inherit the default permission of the repo or the organization, which, if they haven't been explicitly set and the organization has been created before a certain date, I think in 2021, it would be by default read-write. So most organizations that have been out there for a while that have open source projects, unless they specify explicitly the permissions, the workflow will get read-write, which means that they can modify the code, for instance. Also, the kind of dependencies that can come into play in the workflow, you can have, in some cases, containers. So that is an example where the workflow itself would build upon some existing Docker container for exposing some tools at runtime. In this case, what's also important is the fact that it pulls the code coming from the pull request, and it takes the kind of untrusted code coming from the fork. So there are different ways to do that, some of which are secure or safe, but this one is definitely the most risky. And if you end up with that kind of configuration, basically anything that runs after that could be compromised. So in this case, you're running make, which make is going to be looking for a make file. And if the contribution, the untrusted code coming from the fork, contains a malicious make file, then it's game over. You will have like arbitrary code execution. Another scenario is at the bottom, you see this $, curly brace syntax. That is a way to effectively refer to build time variables, which in this case is the head ref, so the Git branch name coming from the fork, which the attacker has the ability to configure arbitrarily, so they can give their own branch name on their fork arbitrary name, as long as it satisfies the requirements or the constraints of a Git branch, which in fact is more than enough to perform Bash or JavaScript injection. So let's look how to analyze this type of vulnerability at scale. So how we've done that internally, we've built a project that we've called package supply. So package supply was started about a year ago by being seeded with over 350,000 open source projects. Now we're well over 1 million projects that are indexed. We had a big focus on Terraform modules and providers because we thought that previous research was not putting much emphasis on that. And I'll give a concrete example in a moment. So what we do, we basically scrape and index the repositories. We find any build pipeline in it. We effectively parse and index that in some database. We run static code analysis to find vulnerabilities in those workflows. And any build component we identify over the course of this indexing will feed back this package supply system so that we organically discover new repos and packages and then new workflows that may be vulnerable. So everything gets ingested in a big data database, namely BigQuery, that is very useful to analyze at scale. So that also helps us to further improve our statistical analysis by retroactively finding vulnerabilities that the SAS didn't find at first. And we use also graph database to consider more complex attack scenarios. So if we look at some numbers, last spring, we had about 350,000 packages in the system, out of which the vast majority were just run-of-the-mill open source projects, but you can have some idea of the number of GitHub actions and Terraform modules and providers we were specifically ingesting. About half of those were using GitHub actions. And the vast majority, if not the entirety, were not explicitly setting the permissions for the workflow. So they would inherit the default permission, which in many cases would be read-write. So if you start with that premise, and then you kind of narrow it down to the workflows that trigger on risky actions, risky events that effectively expose the secrets during build time, then those that have injection, or those that that have the an opportunity to misuse build tools, there is a fair number of projects that we found to be vulnerable. So, but now if you put that into a graph database, you can start to think about attack paths that are not direct but transitive. So if we find, let's say, a GitHub action that has a vulnerability, and that GitHub action is used in other workflows, and those workflows, depend on that GitHub action transitively. So you can build so-called composite GitHub actions. So in that case, the blast radius or the impact of that one vulnerability is that much greater than it may seem at first. So again, we talk about CVEs and dependencies, or 0 days in dependencies. But when you focus on build dependencies, the interesting thing is that there are not only 0 days, but there are 0 days that haven't been exploited yet. So there's just an opportunity to go compromise that workflow, and even more so in transitive build dependencies, the blast radius of that potential compromise can be that much disastrous. So we perform a number of coordinated disclosures with big and small open source maintainers. So we have some ideas of the bug bounty that we had a chance to work with. So Google was very generous, in fact, in the last September. So we found about 22 repos owned by Google that were vulnerable to something similar to that. But we found in the past year, we disclosed to about 50 or so organizations, and we continue to find more and more. So the interesting thing that we saw as we were finding more and more is that there were some patterns, like things that we would see more and more. So the build tools that would come in those build pipelines, and that were responsible for the actual vulnerability, were, so we would start to see patterns, and we built this project called Living Off the Pipeline. So I'll tell more about that in a moment. So in the example of Gunplate, so you can find, in fact, this Living Off the Pipeline project on GitHub. It has different pages for different build tools. And Gunplate is a template rendering engine written in Go. The interesting thing is that if you look at the documentation of Gunplate, you'll see that you can not only configure it using command line parameters, but also using a config file. So the .gunplate YAML file, if you have it in the current working directory where you execute Gunplate, you'll have an opportunity to execute arbitrary commands simply by adding them to this config file. So I'm going to show you a concrete example of an attack scenario that we've disclosed now. It's more than a year and a half ago, but I can tell you that this attack scenario applied to modules, very, very popular modules, Terraform registry, that were downloaded millions of times. So if we look at Terraform, the Terraform registry, there are providers and modules. The interesting thing about modules is that they themselves can have dependencies. So that's much more interesting than just providers, because providers don't necessarily have the concept of dependencies. And modules are no more, no less than a public GitHub repo, which has an association in the Terraform registry. Terraform itself was simply git clone that repo when it executes. So if we look at the Terraform registry in this example, we have module A that depends on module B. At the moment, it's version 1.09 that's published. And I'll explain the attack scenario, which starts by forking the Terraform module B, opening a pull request that contains a malicious contribution, in that case, a malicious .gunplate YAML file. Or it could be, in some cases we've seen, with malicious Git branch name. So as the pull request is open, it triggers a CI test. And in that case, there's a vulnerable GitHub action, which allows the attacker to execute this malicious command in the Gunplate file and ultimately backdoor the Terraform module B. So I'll show you, in fact, live. Well, it's not a live demo, it's a recorded demo, but still in real time. So we have two modules published to the Terraform registry, one of which is module 1.0.0 that has a dependency. So that other module, if we look at it, currently it has version 1.0.9. And if we look at the corresponding GitHub public repo, indeed, there's that version. So in that case, the victim is using Terraform normally, and the victim depends on module A. So they might not even know that module B comes into play. So the attacker has everything scripted. So it lasts about 20 seconds. So what the script does, it will clone, fork, and push the malicious gunplate in the fork, then open a pull request. And by merely opening the pull request, it will trigger the GitHub action. All right. So we can see that GitHub action is running. We can see the malicious gunplate commands. Looking at the logs, we can confirm that in about 14 seconds, the attack has succeeded. So at that point, the module B has already been backdoored, and the attacker has the ability to clean up. So in that case, they force push, which removes the malicious commits, leaving not much to be seen in the pull request itself. So if someone were to look at the releases, they see that there is a new malicious module published. And someone that would like to audit the code in the repo would not find the backdoor in the main branch. But if they had a careful look at the new release, they would notice that the tag is pointing to a commit, which is not part of the repo itself. So it's a dangling orphan commit that came from the fork. So the victim will be running Terraform. In that case, they don't even need to do a Terraform apply. Simply a Terraform plan would be sufficient to pull the latest malicious version of the module. And in a few seconds, if you notice at the bottom, you see that the Google Cloud superadmin token was exfiltrated. So if we go back to the slides. So what can you do? As I mentioned in the beginning, threat modeling your build pipelines using SLSA. That gives you kind of a full picture of your development environment, not just the production, but also the build environment, which may contain dependencies and potentially the vulnerabilities. You want to inventory the dependencies, not just in your final artifact using an SBOM, but produce an SBOM of the build pipeline. You want to apply the least privilege principle also in the pipelines so that you limit the amount of secrets that are accessible to it. And using branch protection is really the cornerstone of protecting source code repositories. So you need to start with that, like make sure that some branches are considered clean, having been code reviewed, and they don't contain anything suspicious. And that will further prevent, it will make it harder for someone to automatically push code to it, or at least that you have some opportunities to set some criteria before that happens. You can run static code analysis on those build pipelines. I'll tell you more about that in a moment. And there are also runtime protection solutions that are specifically tailored to build pipelines. So how do we find this type of vulnerabilities? So in the spring, we introduced an open source tool that we called Poutine. So as I mentioned, our company is based out of Montreal, Canada. So poutine is, our local dish. And we thought that it was only fitting because poutine in French has this meaning of messy. So when we look at build pipelines, often it's a bit messy. It's not really, the quality of build pipelines is not as high as the production code. And so it is an open source static code analysis tool that is specialized for build pipelines. It currently supports GitHub Actions, GitLab, Azure DevOps, and Tekton pipelines. There are about 12 rules, many of which would cover the scenarios that I discussed today. It's very efficient. You can run it even on fairly large GitHub organizations that contain hundreds, if not thousands of repos and get results within just a few minutes. So you can just as much integrate it as part of your own CI/CD process to self-check your own build pipelines. So we use it as a core part, effectively as a library to build this infrastructure that I discussed. And we continue to evolve it. And now it is effectively kind of a commercial product that we offer to large open source companies. So you can use it as a command line tool. It's very quick. You just give it a read-only token, and you can output the results directly in the command line or output as JSON. There is also a capture the flag thing that allows someone to learn more and like practice how to exploit those build pipeline vulnerabilities. It's called Messy Poutine. You can find it on GitHub. It contains about 25 challenges, which allow you to really kind of know the different scenarios, including the one that I demoed of exploiting a Terraform module. So how to remediate this type of vulnerability? If you're using GitHub Actions, there are GitHub Action organization and repo level settings that you want to start with. So the hardening best practices would be to limit the number of GitHub Actions that can execute to well-known, like validated GitHub Actions that you need and are safe. Also, you want to configure the default permission in the workflow so that it is not read-write, but by default would be read. So then the workflow would need to explicitly request read-write. So it's still possible to have this kind of permission, but you would not get it by mistake. And if you're not using self-hosted runners, it's better to just disable it because in that case, it's that much more complex. You need to harden the runners and all that. So how to apply the least privilege principle? Again, like you start by setting the default permissions, and then you still explicitly set them in the workflow. Ideally, kind of in the same way you would do for a firewall, you disable any permission, then you gradually add back those that you need and those that you need for each job. So you would construct your build pipeline by different jobs that would go in sequence, some of which don't even need access to code maybe, or they only need read-only access. Some parts might need access to secrets, but not others. When it comes to secrets, there's a concept of environment secrets for GitHub Actions, which allows you to set extra conditions before the secrets are accessible at runtime. So you may add explicit manual approval or time delays and other things. Whenever you want to interact with external services, for instance, cloud providers, instead of having not hard-coded, but like long-term secrets, it's much better to use short-term ephemeral secrets using OpenID Connect, and that is supported by most modern build pipeline systems. For the workflows, I mentioned some workflow events that are more risky than others. So the pull request target, for instance, and workflow run issues and issue comment are kind of the main ones that you want to pay extra attention. So for those, you want to make sure that you audit the code if you really need it. But otherwise, I would recommend to just use pull request instead of pull request target, as it's much safer. It doesn't expose the secrets when it's coming from a fork. Any kind of injection scenario, you want to pay more attention. So ideally, you just simply want to avoid the interpolation of variables, at least not directly in the context of scripts. You want to first interpolate in an environment variable, and then you just use the environment variables. For any kind of build tools, I mentioned Gunplate. You can have a look at the Living Off the Pipeline project to learn more about other tools that can be risky. When it comes to the runners itself, like it's much better to use the ephemeral hosted runners that GitHub provides. But if you need to use self-hosted runners, and if you have a good reason to do so, there's a number of best practices to harden those self-hosted runners. And it's because otherwise, like the blast radius of any compromise can be that much greater as you would, maybe have a direct access to a cloud environment. There are runtime protection solutions such as Steps Security Hardened Runner, which allows you to set effectively firewall rules and other kind of hardening methods, as well as have some telemetry to perform forensics, for instance. So to recap, build pipelines are quite complex. It's an area of research that's still much underappreciated. We're just starting to scratch the surface. The statistical analysis tools, for instance, that we published is still quite simplistic. It has a number of false negatives, but even that, then we still find a number of vulnerable pipelines in popular open source projects. So as this matures, there's less low like. For now, we're focusing on low-hanging fruits, but as time goes, we know that there is more to be found. So we think that people should be more proactive versus reactive when it comes to this type of attack scenario. There are tools like I mentioned, Poutine, that you can find and try. So in fact, there are more resources that I invite you to look at. We've published a number of articles on our blog. And the projects that I mentioned during the talk, so Poutine, Messy Poutine, and Living Off the Pipeline. If you're interested in this topic, there's a number of other researchers that we collaborate with that did conference talks in the past year about GitHub Action compromise also. Namely Adnan Khan at the DEF CON 32 talk was really good. So I invite you to have a look at that. Thank you.
Thank you so much. That was amazing. Just Steve, Frank, and I had a bit of a really fascinating conversation in the background there, just discussing some of the stuff that you were talking about. It was amazing stuff. So thank you. Does anyone have any questions that they'd like to post on YouTube or on LinkedIn? We are happy to take questions, or even just in the chat here.
I think I see one that says like, what's a malicious Git tag? Yeah, so malicious Git tag would be or a malicious Git branch. So basically any Git reference. The simplest scenario would be the branch name of the contribution coming from the fork. So the attacker forks the repo, they set the branch name on their side, and as long as it meets the constraints of a Git branch name, which is effectively 255 characters without spaces, and then you can even have emojis if you in a Git branch name. No spaces, that's basically the hardest constraint, but it's more than enough to put $, curly brace, whatnot, IFS, like the line separator, to kind of bypass this limitation. That's enough to add the bash code. Same thing for JavaScript. And I think, there's some links that were shared. I see that some folks use the Terraform, Jenkins, Bitbucket. Basically, the scenarios that I explained, they apply not just to GitHub Action. It's basically the same idea on Jenkins, GitLab, Bitbucket. As long as you accept external contributions and CI/CD runs automatically as soon as a new commit comes in, you need to consider those scenarios. So,
I have a question. So you mentioned it's difficult to create what would be considered an SBOM. People know what that is in terms of their own software and their own dependencies, depending on what the language is. But in terms of the CI/CD pipeline, not so straightforward. how would we go about doing that? Is there an open source solution, or are we looking to commercial solutions? What do we do about that?
So the open source tool that I mentioned, Poutine, it does produce an inventory of the artifacts it discovers. So that's one thing that exists. As far as I know, I think not Trivy, like another open source tool, it doesn't. But Sift from Encore, it does find GitHub Action components, but it's not as exhaustive as what Poutine does, because Sift is more like a general purpose SBOM tool. So right now I would say Poutine is one that one can consider.
Okay, cool. If you have the link for that and you have access to the chat, feel free to fire a direct link to Poutine to the chat so people know where to, have actionable things they can play with. I already put the living off the pipeline in there. Just how bad are defaults within GitHub or GitLab or Bitbucket? Because you pointed out a few near the end.
Mm-hmm.
If I do nothing, how unsafe am I? I know the answer to this.
Well, the interesting thing about GitHub is that they're very, they were acquired by Microsoft, but even before they were acquired by Microsoft, they were very careful about any breaking changes. So if you created your GitHub organization some many years ago, or even a repo, you keep the security defaults that existed at the time of creation. So unless you go in and explicitly make the changes, you will not be automatically updated to the latest security default. So they evolve over time, they get better. But if you have even today, like a brand new org you create from scratch, it will have a number of mitigations that I would suggest. But again, like most large open source projects are in orgs that have been created long ago. And in that case, you still need to kind of create vulnerable workflow that is triggering on the events that are risky, right? So it's not like it can be compromised so easily. But if you look at open source projects, in many cases, they want to automate things, not just run tests, but they want to validate, pull request contributions that meet certain criteria. And to do that, you need to expose secrets. And that's exactly when it starts to be risky.
I'll pause for a second, see if anybody else has questions, because they all know that. Well, I know too much about this. We need to do a podcast. We can just talk about it for like 45 minutes.
That's definitely going to happen. There is one question I was going to ask, actually. So during the talk, you mentioned you should use pull request, not pull request target. And you mentioned that the reason for that is because it could expose secrets. I couldn't quite get the link there. Could you just explain that in a bit more detail?
Yeah. So if you look at the workflow, like GitHub Actions workflow, at the top, you'll see the list of events that trigger that workflow. So it's typically called, you see the keyword on, pull request. So that one has, let's say, safer semantics. It will expose secrets only when it's contributions that are internal. So like fellow contributors that have direct write access to the repo that can already git push, create new branches and all that, right? They will get the workflow to run with access to secrets. But at that point, this is more about like using the branch protection to protect like merging to the default branch before some like code review is performed. But in the context of accepting contributions from external contributors from forks, that will simply not, like the documentation says that pull request will not have access to secrets. Even if you kind of mistakenly explicitly ask for it, you will get no secrets. They'll be like blank. Like literally, if you try to access the variable, like you'll get an empty string. In the case of pull request target, you'll get the secrets. So as soon as that's the case, then someone can dump the memory. When you have remote code execution, you have basically sudo. You have like full ownership of the machine running, like it's a ephemeral virtual machine. You can just dump the memory and get all the secrets at once.
Okay, that sounds super dangerous. I'm going to hold off questions because I could go all day, and it is almost 3. Anything else from our the watching crowd or our hosts?
I'll post some of the other links to Gravy in the chat, because it looks like you've got some really like fun resources to kind of get going with.
Very cool. Okay. I'm going to ask one more question, Francois. I looked at living off the pipeline, and it's frightening how many tools you have there. It's also frightening that one of the ones I used to work on is there, Chekhov. But when I look at the Git repo, I see you have a lot of issues because you look like you're going to add just as many more tools to it. Like, how many tools can people take advantage of with this kind of remote code, lesser living off the pipeline vulnerabilities? Is it like seemingly endless?
Yeah, the more you look, the more you realize that most, if not the entirety, of the tools that are typically seen in build pipelines are have some kind of foot gun, has something that makes them unsafe to use, and potentially allow a remote code execution. Well, I mean, basically, like for instance, test tools, basically they are completely unsafe, like because you allow external contributors to contribute the tests that come along with the code contributions. What are tests if not just arbitrary code, right? Or so by default you run arbitrary code. So if the secrets are accessible in memory at runtime during the execution of the tests, and for instance you need test tokens to validate the test, it's very risky.
Very cool. I like watching Jess laugh when you said tests are arbitrary code. That's what. Oh yeah, head scratch.
So,
okay.
but I'm sorry, but to answer your question, yes, there are a number of living off the pipeline tools that I haven't had time to finish. So there's a number of GitHub issues that are like good first issue that people can go in, look. I kind of did the pre-research to set the stage for the part of looking for the documentation of the tool, the foot guns. It's just that need to add the examples and better description. So anyone that would like to contribute is more than welcome to do so. I had some very good contributions a few days ago by a German fellow that was very good. I think his name is Benedict Hausmann, if I'm not mistaken. He contributed some improvements to the Terraform article, which I thought was brilliant. So hoping to get more contributions like that.
Okay, cool. I see people dropping off the line because it is nearing the hour and people probably have things to do. Are we all good here?
Yeah, that was great. Thank you so much for coming along, Francois. That's been an amazing talk tonight. I feel that even though we didn't get many questions on here, maybe it's just a bit of fear, but I've got a feeling that we're going to get a lot of questions over the next few days, and I'm sure Steve, Jess, and I will probably jump on a podcast with you to ask you some more questions in the very near future. So I'd just say to people, look out for that, because I'm pretty sure there's going to be a lot more that we're going to discuss. So yeah, thank you so much, Francois, for coming on tonight. Thank you to all of our viewers on LinkedIn and on YouTube for tuning in. It's been an amazing to see you. And I think, Frankie, you just wanted to say something?
No,
Oh,
thank
no, I
you.
was just going to say
Oh, sorry. Go ahead.
I was just saying thank you as well. Sorry, thank you, Francois. Over to you, Francois. Thank you so much for joining us. It's been amazing. And I think all of the praise in the chat is evidence of that. So thank you for putting on such a great virtual event.
Yeah. And don't forget, our next event is in person on the 15th of January. And all I can say is AI.
Hey.
Okay.
Okay.
And with that, we'll wrap it up. Thanks, everyone.
Thank
Thanks,
you.
Francois.
Bye-bye.
Have a good one.